If you're a human person, one of those things you're going to want to do with some regularity is boil water. We do it for lots of reasons, from cooking to cleaning and disinfecting to other things probably. And one of those other things is preparing hot beverages such as tea. Maybe you'd file that under cooking, I don't know, it doesn't matter. Anyway, this is such a common practice in the daily lives of humans across the planet that purpose-built water boily-pory things called kettles are quite a common sight. But they're a little less common here in the US than they are in many other parts of the world, particularly the electric variety. Actually, I think it's fair to say that they are a lot less common. One often cited reason is that our 120-volt electrical supply just doesn't have the gusto to make electric kettles worth it. Look, here it's cited 3 times. But by the end of this video, I hope you'll learn, as I have, that this just isn't true. Electric kettles are, even though they are a lot slower on this side of the Atlantic, still significantly faster than their stovetop counterparts. At least, for now. Spoiler alert, there's a twist. I'll begin with some testing and demonstration. As a note, the times I'll be referencing in this video came from off-camera tests. I'll replicate some of the tests on camera, but the results will probably be slightly different. This is my stovetop kettle. It's red! And it has a wide, flat bottom, which is helpful for doing tests because it'll work great with any stove. Throughout this video, I will be bringing this much water to a boil. Yes, this is a SodaStream bottle. It was convenient. Anyway, this is pretty close to 1 liter, but not exactly. The most important thing is I'm being consistent with each test. The water will come straight from the tap and will go into a cold kettle, and we'll time how long it takes to boil. For this kettle, I will consider it done when I hear the first peep from its whistle. On this gas stove's normal burner, it took a glacial 7 minutes and 40 seconds to come to a boil. This stove does have a higher power burner available, but we'll get back to it in a bit. Not everybody has a gas stove though. And if you don't, you might want to consider yourself lucky, but that's a topic for another day. I brought the kettle and my measuring bottle along with me for a visit with my parents. You see, they have a glass ceramic electric cooktop. I don't know what the exact power output is of the burners, but I do know that the entire thing is 8.8 kilowatts altogether, and with these burners being the average size of 4, I think 2 kilowatts is probably pretty fair. This burner, from cold, brought the kettle to a boil in 6 minutes flat, which actually surprised me. I figured it wouldn't be as fast as my gas stove, but it actually beat it by nearly 2 minutes. Go figure. Now let's see how an electric kettle will do. This is the cheapest kettle you can buy at Walmart. And as you can see, it sports an exquisite design and is built of the highest quality materials. Like virtually all electric kettles, this sports an automatic shutoff feature. However, there's a substantial delay between when it begins to boil and when the shutoff is actually tripped. So I'll be considering this kettle done the moment it's at a roaring boil. How long does this fella take to boil that amount of water? 4 minutes and 33 seconds. I suspect some viewers are aghast at that performance, but that's more than 3 minutes faster than the stovetop kettle on a gas stove, and about 1.5 minutes faster than the same kettle on a glass ceramic electric stove. Why might that be? Well, the answer is pretty simple, but before we get into it with excruciating detail, let me reiterate that the cheapest electric kettle I could get my hands on is significantly faster at boiling water than this stovetop kettle, despite being limited by our 120-volt electrical system. Our weird system puts a practical limit of 1500 watts on most things which plug into ordinary outlets, although 1800 watts is technically permissible, and on a 20 amp circuit, which is fairly common, especially in kitchens, 2400 watts is possible, but since it's by no means universal and requires a different plug to be compliant, most devices stick to a 12 amp limit, which nets 1500 watts at a slightly optimistic 125 volts. That's plenty of power for virtually anything, but many of you in 230 and 240 lands will find this kettle to be obnoxiously slow. I've also seen a few people here who have installed a 240 volt receptacle in their kitchen specifically to use with imported kettles. and I guess more power to them. Just a reminder, we actually have 240 volt power here, but we do it weird. I made a video about it if you want to learn more. Now, hot take, all y'all tea drinkers are fretfully impatient. Oops, did I say that out loud? Anyway, with the knowledge that even a cheap little kettle with our weak little plugs is still a lot faster at boiling water than a kettle on a stove, why aren't they the household staple that they are in other parts of the world? What a perplexing mystery. I doubt we'll ever know the true answer. It's because we don't drink tea all that much, you guys. That's it. That's the answer. It's not like nobody here drinks tea, but I think it's fair to say that for the majority of households, tea is more of a, ooh, I'm feeling fancy today, let's whip out the Earl Grey kind of a thing. It simply is not the cultural staple for us that it might be for you, especially in the context of, say, social gatherings. When friends come round, putting a kettle on is not really in our cultural vernacular, but brewing a pot of coffee absolutely is. So, since most of us find ourselves boiling water for tea only occasionally, if ever, a faster, purpose-built water boily-pory thing is just not on the average American mind. That's all there is to it. Yes, our electric kettles are slower than they are on the other side of the Atlantic, but they're still the fastest way to boil water. The trouble is that relatively few people even know to want them. So why is this $15 lump of plastic so much faster at this whole water boiling thing? Well, take a look inside of it. We can see the heating element. That's it. That's the thing what get hot. And when you fill it up with water, the heating element becomes submersed in and surrounded on all sides by the stuff we're aiming to heat. All of the energy that this thing can pull from the wall is getting dumped straight into the water, save for whatever tiny bit is lost in the power cord. Many electric kettles don't have an exposed heating element like you see here, but instead bond the element to the bottom surface of the kettle, which the water sits atop. It's a different arrangement, but the effect is much the same. In comparison, a stovetop kettle can only try its best at absorbing heat that's getting blasted at it from below, and then transfer that heat into the water it contains. That's just much less effective than releasing heat directly into the water. How much less effective is it? Well, we can find out pretty easily with some math. One fun thing about this universe is that energy is energy. We have a lot of different names for it and measure it in a bunch of different ways, but it's all the same thing, and we can convert between units easily. One of those units, which is particularly useful for this discussion, is the calorie. That's how much energy it takes to elevate the temperature of 1 cubic centimeter, or 1 milliliter, of water by 1 degree Celsius. If we presume that the water from the tap is at about 20 degrees Celsius, and we have 1,000 cubic centimeters of water to raise up by 80 degrees, then it will take 80,000 calories of energy to bring it to a boil. Now we can ask a search engine to convert that into a different unit for us. Let's go with joules. No, I didn't want the kilocalorie. That's what we commonly use for food. I just want 80,000 calories, the regular kind. Fine. 80 kilocalories is 334,720 joules. Why have I chosen joules? Well, here's a fun thing. You know what the watt, the commonly used unit of electrical power, actually is? It's 1 joule per second. And since our electric kettles typically run at 1500 watts, that means they can put 1500 joules of energy into the water every second. So if we divide 334,720, the number of joules we need, by 1,500, the number of joules we can add to the water every second, we will find out how much time it should take for an electric kettle in the US to boil a liter of room temperature water in seconds. That answer? 223. In the real world, though, it took about 22% longer than that. Our theoretical speed is 223 seconds, but the observed time was 273 seconds. What's the cause of the discrepancy? Well, actually there are two causes. First, this thing doesn't actually pull 1500 watts from the wall. It's a resistive electrical load. The heating element is just a giant resistor after all, so the actual power it consumes will depend on the voltage at the receptacle. In my test, it was drawing only 1,430 watts. Knowing that this was the real power output, our theoretical time should be revised to 234 seconds. Our observed time, though, was still about 16% longer than that. Why? Well, it's not just the water that we're heating. The body of the kettle itself gets warmed up through the water, and that thermal mass slows us down a bit. Plus, of course, some energy escapes into the room before the water boils, both through the sides getting warm and a bit escaping out the top. Still though, only 16% more time compared to literal perfection ain't bad. Let's switch things up a bit. Remember, energy is energy, and we can convert the 80,000 calories it takes to lift a liter of water by 80 degrees Celsius into watt-hours. Joules are fun and all, but since we tend to measure power output in watts, it's usually easier to conceptualize energy in watt-hours. Plus, you get much smaller numbers, which is helpful. 80,000 calories is about 93 watt-hours, according to Google's Converti-thing. How many watt-hours did our kettle use? Well, 273 seconds divided by the 3,600 seconds in an hour, and then multiplied by the 1,430 watts the kettle was actually pulling, tells us that we consumed 108.4 watt-hours, which is, what do you know, about 16% more than 93. Ain't this fun? Let's do a little more math. Through the magic of buying two of them, I have a second, slightly fancier kettle, and this one sports rapid heat technology. Which is funny because it's only rated 1100 watts. This one has the embedded heating element design. Rather than a big curly thing getting hot, the bottom surface is what gets hot. Given what we've learned, we should be able to predict how long this will take to boil a liter of water. Let's see, 334,720 joules divided by 1100 watts is 304 seconds, or just over 5 minutes. I'll go ahead and presume the same 22% overall discrepancy from the cheap kettle, accounting for both a slightly lower than advertised power level and also the energy needed to heat the kettle itself, and predict it should take about 371 seconds, or 6 minutes and 11 seconds. Let's see, how long does it actually take? Oh good, blue LEDs. My favorite. And it actually took 6 minutes and 13 seconds, proving once again that energy is energy and water is water. So now let's take a look at the gas stove and stovetop kettle again. The burner, which took 7 minutes and 40 seconds to bring this to a boil, is rated 9,500 BTUs per hour. Oh good, another unit. Now, in this context, as is often done with the BTU for whatever reason, the manufacturer is using a unit of energy to convey power, which is a bit confusing, but it is what it is. I don't have a way to verify its performance, unfortunately, but if we assume the burner is performing to spec, the 9,500 BTUs per hour can be converted to instantaneous wattage, and thus this burner outputs 2,785 watts at full power. You may already see the absurdity here, but let's keep going and work it out. It should take only 93 watt-hours to bring a liter of water to boil. This electric kettle, with a modest loss, took 108.4 watt-hours to do it. The second electric kettle, with a lower power rating, did take longer to do the job, but required a nearly identical amount of energy. This thing, sitting over 2,785 watts of fire, manages to take more time to boil than either electric kettle, 7 minutes and 40 seconds. That works out to 356 watt-hours of energy consumed. That's astoundingly bad, nearly quadruple what's theoretically required, and more than triple what the electric kettles need. But it's not really surprising, is it? I mean, this is just a cold object over an open flame. Of course, the bulk of the energy being released as the fuel combusts is just going around the kettle. If you've ever used a gas stove, you've undoubtedly felt how hot the air is above the pot or whatever. That's all the heat from the flame which isn't ending up in what you're trying to heat. Sure, some of it's making it in there, but in the case of this kettle, apparently not even a third. This stove also sports a quick boil mega burner, which outputs 17,000 BTUs per hour, or 4,985 watts. This thing is so powerful, flames lick up the sides of the kettle. On this mega burner, the time to boil decreases to 4 minutes and 32 seconds, which as it happens is exactly 1 second faster than the time recorded by this electric kettle. But that time savings comes with even less efficiency, as the total amount of energy needed to boil a liter of water on this burner climbs slightly from 356 to 376 watt-hours. Oh, and by the way, 376 watt-hours isn't just a lot of energy to spend boiling a liter of water, it'll also make your kitchen quite a bit warmer, which is great on summer days. Oh, also, the heat from the flames licking up the sides makes the handle too hot to touch with bare hands, so that's fun. There's been a lot of talk lately about how gas stoves are just, well, kinda bad for lots of reasons, and I gotta say this is revealing yet another reason. I mean, if it takes more than triple the energy output of a 1500 watt electric kettle just to match its boiling time, all I can say is yikes. Let's go back to the electric stove and see how well it did from an efficiency standpoint. If we assume that this burner was outputting 2000 watts, then the required time of exactly 6 minutes, which is exactly 1/10 of an hour, meant 200 watt-hours were spent boiling the liter of water. That's still much more than the electric kettle's 108, but nowhere near as bad as the 356 required by the slower gas burner. Putting the kettle in physical contact with the thing that gets hot seems to transfer heat energy much more effectively. For grins and giggles, I timed this little hot plate. It only outputs 900 watts, so it took a while. 13 minutes and 8 seconds, in fact. Let's do the math though. This thing really only outputs about 870 watts, according to the kilowatt. 13 minutes and 8 seconds at that power level works out to 190 watt-hours. This was definitely slower than the 2 kilowatt burner, but it was a tad more efficient. At least, I assume so. Probably because the glass ceramic cooktop works almost like a heat lamp pointing up at the kettle. It's blasting infrared light at it, and since the kettle is just a little bit smaller than the total area, some energy is making its way around the kettle's sides. This burner, though, is simply getting real hot thanks to a heating element inside of it, and with the kettle in physical contact, a slight majority of that energy ends up getting absorbed by the kettle and into the water. Not bad. This probably means that the old-fashioned curly Q burners might actually be the best conventional electric burner design, at least when it comes to speed, since they have relatively little thermal mass and the element itself stays in contact with the cookware. With everything we've seen, I think it's clear that if you want to boil water conveniently and quickly, the electric kettle remains your best option despite our weedy little plugs. But this may be about to change. Thanks to induction technology, the stovetop kettle can be even faster than an electric kettle. In fact, potentially faster than a European one. Induction stoves are the new hotness, and they work by sending high-frequency alternating current through a coil of wire beneath the cooking surface. When a suitable cooking vessel is placed above it, electric currents are induced within the vessel's metal base. Those currents will actually heat the bottom of the pot, or what have you, just like the current flowing through a heating element. In effect, it turns the pot itself into the heating element. Now, I don't have an induction stove, but I do have this plug-in induction cooktop. This thing is not shy of pulling the full 15 amps from an electrical circuit, and on full power it consumes just about the 1800 watts that it claims to. Now, there's some waste in this process. That's why this thing has a cooling fan in it. So I don't know exactly how much is actually getting transmitted into the kettle. But at full power, this brought a liter of water to boil in 4 minutes and 29 seconds. That's the fastest result we've seen, suggesting at least 1500 watts is making it into the water. And keep in mind, this is limited to what comes from an ordinary electrical outlet. The hardwired induction cooktops you'll find either on their own or attached to an oven often feature a burner, or I guess a better word is emitter, that can pump out close to 4 kilowatts, sometimes more. With one of those, you could boil a liter of water in 90 seconds flat. Still, speed isn't everything. One very handy feature of nearly all electric kettles is that automatic shut-off. That does give them an element of safety which is missing from a stovetop kettle. I think there's a certain charm in household objects that scream at you when they're ready, but I'll admit a more silent option is nice. Plus, unless and until I get a proper induction stove, this remains the fastest... Okay, this was a little bit faster, but the most convenient and efficient option for boiling water. Though I don't often drink tea, I've kept a kettle around because it's just too handy. Even if I'm making pasta, it's faster to fill this up, bring it to a boil, and then pour the water from it into a pot on the stove than it is to use the stove to boil the water. Which is nuts, but it's the truth. Plus, the kitchen doesn't get nearly as hot when you do that, and I don't have to run the stove as long, which is great for indoor air quality. I should make a video about that too. It's astounding how bad these are. It's almost like combusting fossil fuels inside of a living space is a bad idea. Aside from that great benefit, there are also fancier kettles available which let you set them to a specific temperature. Great for certain types of tea or really pedantic coffee enthusiasts. And if you're really bothered by waiting 4 minutes for boiled water, there are a few solutions that are much less involved than rewiring your kitchen. First, and here's a wild idea, just don't fill the kettle up all the way. It takes more time to boil more water, and if you're just making a cup for yourself, only fill the kettle to the minimum mark. On many kettles, that can be as little as half a liter, which only takes a hair over 2 minutes to boil, even with our pathetic little plugs. But watch out, as there are kettles out there which don't operate at 1500 watts. Like this one. It may look nicer than the cheap Walmart kettle, but it's definitely worse at being a kettle. Ooh, but it did come with this free loose leaf tea infuser, so that's nice. Another option you might want to look into if you're particularly impatient is something like this. You're right, this isn't a kettle, but you could call it better than a kettle. These... well, I don't know what the proper name is, but boiler, warmer, and dispenser all seem like common words, so let's go with hot water dispenser. These hot water dispensers feature an insulated tank which they will diligently keep at your desired temperature. Many also feature timer functions to allow you to set when you want them ready, so they don't waste much energy when you don't need them. Use one of these and you don't ever have to wait for a kettle, and they actually only need 700 watts. There might be some merit to keeping an insulated tank of water around, rather than pumping 3 whole kilowatts of heat into cold water whenever you feel like it. Anyway, that's all I've got for you with this video. This whole kettle discourse is so wild to me. I get it, you've got 3 kilowatts of water boiling power at any outlet. It's gotta be kind of annoying when you make a visit to this continent, or worse, move here, and suddenly it takes a whole 2 more minutes to boil a liter of water. I mean, you poor things. But I do want to point out that I think it's kind of hilarious how, aside from electric vehicle charging, boiling water quickly is about the only practical benefit to having that much power at any receptacle. This is the one thing that seems to get stuck in the craw of lots of folks regarding our electrical system, which is just... that's kind of funny to me, that's all. Don't get me wrong, there are plenty of objectively terrible things about our electrical system, but even here, unless you've got an induction stove, this is still the fastest way to get a cuppa. Which actually, I brought the kettle and my measuring bottle with me for a... no, that was correct. I brought the kettle and my measuring bottle along with a... same thing. And we can convert between units easily. What? Yeah, I'm gonna throw that out. I don't like how that went. How many watt hours did it take this kettle to boil? But since we tend to measure power output in watts, it's usually easier. It's just not the average poop.